and automated input. But before I begin, I wanted to share a customer incident with you guys. So just to warm up the crowd and give you a perspective of what we're going to talk about and just some cool stuff. So a client approached us with an interesting problem. One of their customers had been scammed out of a few £1,000s. And the way they did that was they apparently hacked their banking app, mobile banking app. So the client's problem was this customer was having issues with their mobile banking app. And a scammer volunteered to help them with their mobile banking issues. So a scammer sets up TeamViewer on this customer's computer and then gets the customer to connect their Android phone and authorize ADB. So basically, they've got a TeamViewer session set up on their Android device. The scammer then gets the customer to unlock their mobile banking app, leave the mobile device connected, and come back in an hour. An hour later, the scammer has made off with a few £1,000s. And the clients ask us, well, how did they pull that off? And I pose this question to you guys. Do any of you know as to how the scammer might have made off with a few £1,000s by hacking the mobile banking app? That's one way. Any other? Cool. So, yeah, you are potentially right. But there are a few other bits in there that we'll discuss further on in this presentation. So, yeah, my name's Amar Menezes. I'll be talking about screen recording and automated input on Android. So, why should you care about this particular presentation? So, I wanted to share you an attack vector that people haven't explored before. It's an interesting attack vector, and I want to talk about the research that I've been doing in this particular area, and to get some of you guys interested in doing your own research in this area. If research doesn't interest you, and why would you want to get involved, then there's a lot of low-hanging fruit that people can find evaluating the attack surface of this particular vector. And Google's vulnerability program rewards researchers handsomely for even silly bugs that people find. And if research or bug bounty hunting doesn't interest you, then there's this awareness that I want to generate about this is another avenue that people are trying to attack Android devices. So a bit about me. I'm a mobile security consultant at MWR. I advise clients on how to build secure mobile applications. In a previous life, I was a smartphone malware analyst. So I looked at Android malware and understand various techniques that malware authors build into their Android applications. And also in my spare time, I do a bit of Android vulnerability research. So what are we going to cover today? So first, I'm going to start off by setting some goals as to why did I take on this project, what were the objectives of this project, and how I went about achieving that. Instead of just talking about the various bugs I found, I want to talk about the methodology, how I evaluated the attack surface, identified different endpoints, and how I go about constructing a proof of concept. And finally, I'd like to talk about the things that I couldn't look at in this time-boxed research week that I spent. But I'd like to share those ideas with you guys so some of you can take them up, go find bugs, and then share it with the community. So let's start by discussing what were the objectives of this project, what I was looking for, and what did I want to prove. So the first thing was to look for screen recording. What are the different features that the Android system provides you to record the user screen? The second one was once you've recorded the screen, can you generate user input? Can you emulate touches, swipes, pinches on the device? And how do you do that? And if you can change these bugs in screen capture and recording, then that's a powerful capability. So imagine you can capture the user's screen, watch them unlock their banking apps, pull out their PIN, and then emulate touches to then unlock that with this captured PIN. So once you can interact with this app using touches, you will then be able to do a lot of things, such as transferring funds or grabbing your 2FA tokens and various other bits. So a brief recap of the Android security model and specific things that are applicable to this particular attack vector. The first one is all applications on an Android device are sandboxed. So an app cannot interact with another app unless it uses some predefined IPC endpoints. So these are your activities, your services, broadcast receivers, and content providers. The second thing is permission model. So every Android application defines a set of permissions that allow it to use various features on the device, whether it's the internet, Bluetooth, read writes to the SD card. And finally, the Android OS in itself implements a SE Linux policy. So even if you're running under a certain privileged process, you are constrained to certain functionality so that the scope or the context of that process is restricted based on a SE Linux policy. And this will become apparent why these three features or these three particular items are important in terms of evaluating the attack surface. The second goal of this presentation was to make sure that we understand what kind of attacks we're looking at. So we're not going to talk about rooted devices. We want this bug chain or these attacks to work on non-rooted devices, because if you can achieve root on a device, well, one, it's a lot of work, and there's the bug chain to get root on a device is worth a lot of money. So we're trying to look for low-hanging fruit that would work on a non-rooted device, so it frees you from the investment of trying to find an exploit chain that gets you root. The second one is you want to look at only AOSP builds. So these are builds that more or less general across the Android ecosystem. So the Android ecosystem suffers from a fragmentation problem where vendors customize their ROMs before they flash it onto devices. So if we can find bugs that are in the AOSP builds or in the AOSP source, we can safely assume that these will then transcend into other builds or customized ROMs. We want to look at attacks via apps. So we want to attack the different endpoints via the app layer. So we're not looking for WebKit bugs, Chromium bugs, that kind of stuff, no remote exploits, baseband exploits. We just want to say, we've installed this app. From this point, how do we exploit any of these bugs to get screen capture or automated input? And finally, we want to keep user interaction to a minimum, because the more the user has to interact with that, they could spot like, oh, okay, something's dodgy here. This isn't a legitimate app, or there's something malicious going on here, I'm going to uninstall. So if you keep user interaction to a minimum, the chances of successfully exploiting this particular vulnerability are higher. So now that we've set some expectations that these are the constraints I'm going to work with, this is the objective that I have. I want to record the user screen and try to automate user input and chain them. Now let's look at each of those in turn and understand what is the attack surface. So I'm not a professional bug hunter, so I use my own methodology to try to find bugs, and that's what I want to discuss with you in the coming slides. So the first one is screen recording. So enumerating the attack surface, the first thing that comes across is screen record. So screen record is a binary that exists on your Android devices. It's been around since Android 4 or maybe earlier. And typically how people use that is you connect via ADB, you start running screen record, and it starts capturing your screen. The second one is the accessibility service. So the accessibility service, I think, has been around since Android 1, if I recall correctly. So this feature was added to Android to allow users with disabilities to use their devices. So things like magnifying text, speech to text, text to speech. Some of them are like automating input, reading off the screen, and things like that. And finally, this is a more recent introduction, which is the media projection service. So this was added in Android 5, and it was aimed towards gamers and people who wanted to demo various things on their device. So people would build an app that uses the media projection service and then broadcast whatever's on their device on a different screen. So these were the three things that I looked at. So I spent a week looking at attack surfaces for screen recording and automated input. And these were the first three things that pop up. So the next step is to evaluate these three attack points and understand which ones are most likely to lead to a bug. So how do you evaluate that? So the first thing you want to do is look at the minimum Android version. For each of those 3 points, do they span across different versions? Because the older the version of Android, the more likely you are to find a bug that scales across devices. The second one is permissions. So now to use all these different features, you need to define permissions in your Android app. Once you define a permission, you can then build signatures that look for particular features or particular permissions within the Android app and flag it as, oh, this is malicious or this is benign. So if you don't have if you don't need to define specific permissions, it makes for a more stealthy attack. And finally, are there any defenses that application developers have implemented that prevent you from just simply calling a binary or calling an API and just, having a go at the system? So does this require a rooted device? Does it have any SE Linux constraints? Does it prompt the user? Does it alert the user that, oh, someone's going to capture my screen or someone's trying to automate input? And finally, user interaction. What is the level of user interaction that's required in order to use each of these three endpoints? So let's go back and reevaluate these three items. So with screen record, you can invoke this from an application, but the problem is an app runs in a constrained SE/Linux context. So while you can capture anything within your app, you can't capture system-wide recordings or system-wide activities. So, I mean, you'd have to find an SE/Linux bypass or escalate your privileges in order to use this binary. The second one was the accessibility service. Now, if you use accessibility service, you define a permission in your Android application. And once you've installed this app, you then need to interact with the system and enable that service explicitly. So lots of game developers who build bots to bot games use this particular service. And the accessibility service has been exploited in the past. And there's also a cool research paper on how to go about exploiting this with various kinds of overlay attacks. The issue I had with the accessibility service is there's a huge cost to user interaction. So you need the user to step through multiple hoops, try to trick them into tapping on various bits of the screen in order to get this service running. But once you have it, then you can do all this stuff. But I wanted to keep user interaction to a minimum, so I ignored the accessibility service. Media projection was useful, or was interesting, because one, it didn't require any permissions. So you can use the media projection API without defining any permissions. You can run this within the context of your application, so you don't need to escalate to a more privileged context. And finally, all it has as in terms of defense to prevent an attacker from exploiting this is a pop-up. So anytime you use the media projection service, you'll see a pop-up that looks similar to this that says, this particular application is going to start capturing everything that's on your screen. Would you like to continue? So I started thinking, like, well, if this is the only defense, what could I do to get around this? So one of the things was, well, what if I just overlaid this with any arbitrary message? So first thing, call the media projection API. It then calls the system UI pop-up. Once we have the pop-up, we overlay that. We wait on user interaction. And then finally, we can start recording the screen. So when I overlay, it looks something like this. Now, to overlay these kind of UI elements, it's quite trivial. These attacks are not novel. It's been done in the past. Back when Android 4 was a thing, people used toast messages to overlay the screen. The more modern way of doing overlays is to use system alert windows. So system alert windows is a permission you define in your applications that lets you draw overlays within your app. The key thing here is this particular UI element, this pop-up, you can control the feedback loop. So you can control when you've triggered this pop-up and listen for inputs or callbacks once you've tapped on, say, cancel or start now. So if you can control the feedback loop, you can control when your overlay is displayed and when you want to dismiss that. The other thing I want to say is about the system alert window. This particular permission is granted by default. So the user is not one that tells them that, oh, this app's requested this particular permission, unless you actually decompile the app, look at the manifest file. So I want to show you how this works in action. So I've got a demo for you. And because I can't do things live, I've recorded it. And hopefully it plays. Yeah, so what you're going to see here is a proof of concept app that I've built. So the app has two buttons, start and stop. When you hit start, it'll trigger this pop-up. And now this has been overlaid with my custom message. So in a benign app, you'll overlay this and say, well, just download this app, get out of my way, I want to start using it. So in a sec, I'll click start now. And yeah, it's capturing the screen in the background. So here's me just interacting with the email client. That's not my email address, so don't spam me. I did this demo at another conference. It was the MWR briefing. So I've just repurposed it here for this presentation. Cool. So let's look at the recording. So now we've captured this recording. What did we actually see? So we dismissed the pop-up, dismissed the application, and now this is just a recording that the app's made from your user interaction. So here you can see that, okay, it's captured me writing an email to myself. Also notice that you can see key taps. So if this was an app that, say, required you to enter your password, you can record key taps and then reconstruct the password from the key taps. Okay. So now let's talk about exploitability. So we've put together this proof of concept. How believable is this attack? So one, you have no permissions required. So any benign app can call this API. You would not be able to identify just from looking at the permissions that this app requires that, okay, this app can record the screen. Unless, of course, you decompile it and then try to look for API calls. User interaction. So the only user interaction that you require here is obviously install the app and then tap on the pop-up. So once you've granted them permissions, they can capture anything on your screen. So this affects Android devices running Android 5 and above. So the media projection API doesn't exist on Android less than 5.0. And then you rely on rooting a device and all sorts of frame buffer hooking. So this bug has been patched in Android 8. So Android 8, explicitly prohibits the use of overlay attacks. So it prevents you from using a system alert window to draw overlays over system UI components. And if you're interested in the more technical details about this particular attack, how do you control the feedback loop? So I published an advisory. That's a link over here. So you can look at that and then try to build it yourself. So moving on, we have automated input. So now we've achieved the goal of automating, recording the user screen. So now we want to look at how do I replay those gestures, or from whatever I've learned, can I start instrumenting this device or interacting with the device? So once again, let's look at the attack surface. So the first one again is the accessibility service, and like we've discussed before, it has a high cost of user interaction, and people are constantly looking out for apps that define this particular permission. So ignore that. The second one is the input binary. Like the gentleman over there said, you can emulate input by using this binary. So this binary has been around since the first versions of Android, I believe. And it allows you to do different things like emulate touches, emulate swipes, zoom, and that kind of stuff. You can emulate hardware components like a keyboard. And finally, there's system apps. Now, in order to inject events into an Android system, you need to define this permission, which is inject events. This is a system permission that's only found with system apps. So what is a system app? An app that's signed using the device release keys. So once you have an app that's signed with the device's release keys, you can define all these system-level permissions like inject events, and then you utilize the functionality that they provide. So this is particularly interesting because when we come back to the case of the scammer, it's going to be obvious as to why they needed this particular system app, or why did they need this particular permission. So now let's look at evaluating these attack parts again. First one, minimum version of Android. We want to scale our attack across multiple versions, multiple devices. What are the permission requirements to get automated input? What are the defenses in place? Do you need a special context? Do you need, are there any user alerts? Do you need to define some sort of interaction? And finally, there's user interaction. What do I need to get the user to do in order to exploit these vulnerabilities that I might find? So let's evaluate each in turn. We ignore accessibility service for reasons mentioned earlier. System apps. So this is a potential avenue that you can attack system apps, but then they'd be constrained to a specific version of specific ROM, and then your attack wouldn't scale across the Android ecosystem. So you'd only be targeting particular ROMs. So we wanted something that could scale across Android. So then there was the input binary. But the problem with the input binary is if you try to invoke it from an application, you are constrained with the untrusted app context. And so you can emulate input within your app, but not across the system. So the challenge was to find a context that lets you inject input across the system. But we can already do that. So we have ADB. So ADB runs as under the shell context. And using ADB, you can emulate touches and inputs. But it's not that easy to escalate your privileges to ADB. So what are some of the things that I tried to authenticate to ADB? The first one is to use Android APIs to emulate a USB input device. So this didn't work because Once you've built an app that emulates a USB device, your app needs to power the USB bus. So if your app lives on the same device, there are no APIs that can power the bus and then tell ADBD. So ADBD is the daemon that listens for ADB connections. So it can't inform the ADB daemon that, oh, there's someone's trying to connect. Do we prompt them for authorization? The second thing that I discovered was ADB over TCP. So people generally call this ADB over Wi-Fi. What this allows you is to run ADB over a TCP port. So this is something that you need to manually enable. So this doesn't come enabled by default, where you need to connect to the ADB and tell it, oh, listen to port 5555 or any port of your choosing. And yeah, like I mentioned, this is not part of the standard AOSP config. So we are looking for misconfigured devices or devices that have ADBD listening over a TCP port. So there have been reports, let's say that there are tons of these devices that have ADB listening over TCP ports, and you can hit them over the internet. I haven't really looked into the specifics, so I have no real opinion on whether this is a scalable attack. But if you guys are interested, you can read this particular article. It's by Kevin Gossi the dog. Don't know if you know that guy. But yeah, so he had an article about IoT devices that have ADB enabled over TCP. And this is for vendors to push down updates to their devices. So, okay, let's start by constructing a proof of concept. So we know that ADB has a different context, a privileged context that lets you use the input binary to automate input. Assuming a misconfigured device, you want to connect to ADB over TCP. So I build an app, define the internet permission, that lets me connect to the TCP port. Since Android 4.4, ADB prompts you for authorization. So it'll ask you, like, this computer is trying to connect to your device. Do you want to authorize that? And if you grant them authorization, then ADB is authenticated, and then you can start interacting with the system. And if that works, you've got an ADB shell via an app. So here's a demo where I demonstrate the current context the application is, we escalate, and get an ADB session. So here's my app. It prints you the current context. So when I click escalate, it triggers an ADB prompt. So it connects to the ADB TCP port and then says, do you want to authenticate? And once you've escalated, you now are running as ADB shell. So now when you call the input binary, you can automate user input across the device. So exploitability. The first one is the target device needs to have USB debugging enabled. It then needs to have ADB listening over a TCP port. And this particular flaw was fixed in Android 8, where they prevent overlay attacks. But if you get around the overlay bits, you can still connect to ADB over TCP and then try to escalate your privileges. But then, yeah, sure, secure ADB would prevent you to some extent. If you want to look at the technical details of how this was achieved, there's a link there, and you can download that and have a look at the source. So coming back to the case of the scammer. So what actually happened there was the scammer had TeamViewer set up on the device. So TeamViewer allows you to install plugins. Now these plugins are signed by the system's release keys. So different vendors release plugins TeamViewer plugins for their device that lets you, that gives them system permissions. So two permissions that this particular TeamViewer plugin implemented were the inject events plugin and read frame buffer. Inject events allows you to emulate user events like touches and swipes. And the read frame buffer allows you to capture the user screen. Now, most banking apps implement the secure flag. So if you try to capture the screen by traditional means, it's usually blanked out. But if you have access to the read frame buffer permission, you can bypass that secure flag and then still capture the user screen. So that's how the scammer got around it. So they were able to record the user's PIN, interact with the device. So they set up an account, transferred money from this victim's account to their laundering account, whatever. And yeah, that's how this whole thing played out. So case closed. The key thing to remember here is this isn't a vulnerability in TeamViewer. TeamViewer is a useful tool that lets you do various other things. It's just how people use this tool. So yeah, TeamViewer is not a hacking tool. So yeah, in the internet, please don't spread that. Okay, finally, so I've talked about some of the attack surface that I looked at, but I want to talk to you about a few other things that people can investigate and try to find bugs in. And so yeah, I implore you to take up some of this research. The first one is token generation. So when you call the media projection API, and once you've accepted that prompt, it generates a token and says, this token is for this particular application, and it can now go on and record the screen. So if we investigate how this token is generated, look at the various controls that are in place to prevent someone from just auto-generating tokens or spoofing tokens, and we can find bugs in there, then that's useful. The second one is instant apps. In all these examples, you need to have an application installed on the device and then try to exploit the device using this app. Instant app is a fairly recent feature in Android that allows you to point your browser at a link, and that link then generates an app on your device. So it reduces the footprint where you have to install an APK to then start your exploit chain. So if you can get this to work with instant apps, or if there are even more relaxed controls in instant apps, that's a win. I'm not sure what user context instant apps run under, but if it's the same as untrusted app or the default install app, then yeah, there's probably a bit of a challenge. They're looking for SE Linux bypasses. And finally, there might be unexplored and undocumented APIs that you could use. So the ones that I've listed in my presentation are the things that I researched, read the Android, the online documentation, and looked at some other people's research in this particular area. But I'm sure there's lots of things in the OSP source that aren't really documented that people need to spend time looking at and say, oh, well, this looks interesting. Can I change these bugs to achieve the same objective? So yeah, that's more or less it. So I want to wrap this up by just recapping what I've covered in this presentation. The objective, what did we set out? We wanted to demonstrate whether it was possible to record the user screen and then automate input, and maybe chain these bugs together. Look at the various attack surfaces for each of these two vectors, evaluate them, look at things that worked, that didn't work. Try to generate some POCs. Hopefully, if they're good bugs and Google accepts them, you get a CVE at the end of it. And finally, if you do come up with bugs or come up with cool research, share it with the rest of the community. And please tag me. I'd like to see some of that research. And yeah, thank you for listening. Any questions? Really?
So Flag secure, Windows secure, not what I run on the app. So that isn't broken just because TeamViewer has this add-on where you can bypass that. Is that right?
So I can't see where you are, but it's from this general direction. Oh.
So yeah, in case you didn't hear, sorry. So as a developer, I run the secure window so that a user can't screenshot my banking app or malware can't screenshot my banking app. So you're saying it's just TeamViewer's add-on that breaks that?
Yes.
Not stuck Android?
No. So the thing is, the TeamViewer plugins are signed by the vendors. So since the vendors built the ROM, they have the access to the signing keys. They sign these TeamViewer plugins as well. And so TeamViewer, the app, defines these permissions, system permissions that would usually be on a device or a system app. And so, in effect, this TeamViewer plugin is now a system app, and it can bypass most of those controls. So yeah, to answer your question, it's not a problem in Android. It's just the way these guys have built that.
Is that a specific plugin, or just comes with TeamViewer?
It's just the way they've designed the solution. They want it to be as accessible and useful as possible.
Okay, because I've worked for a bank.
Okay.
Where in a slightly different use case than you present, they will literally phone a customer and say, install this quick support TeamViewer on the app, and they'll just walk them through making payments. But we found that the kind of secure elements that we have our app in will black out the screen and sort of anti-debug mode even with TeamViewer on there. So there might be a few variants on how well that does or doesn't work. Hopefully.
So, since that particular incident, I'm not sure if they've discussed this with TeamViewer and tried to add some sort of mitigation in place to prevent people from abusing that. I'm not sure if Android in itself prevents access to read frame buffer. So that's the particular permission you require to get around the screen capture protection.
Right.
So yeah, but it's still something worth investigating.
Yeah. That's fair enough. I mean, as I say, I think we've tested it through an external pen testing party and ourselves, and it seems robust. I mean, obviously for the time being, at least, there's always going to be another way around it, but it doesn't feel as though all hope is lost just yet.
Cool. Thank you for sharing.
Cheers.
Okay, I have two questions, if I may. First one, I heard in another talk the screen overlay thing was fixed also on Android 7. But I don't know whether that you were talking about the same issue. Are there two different issues, maybe?
So there are different ways of achieving overlays. So in the older versions of Android, they would use toast messages. And the more recent one, the more modern way of doing overlay attacks is to use a system alert window. So this one was fixed in Android 8, where if you attended the developer conference, they specifically said apps that define this permission aren't going to be able to draw over system components. So this was in Android 8, so I'm not sure if when you say Android 7, you're referring to toast messages or some other form of...
That was another name, something with S. My memory is very weak. There was a patch probably in Android 7, probably another technique. Sounds like that.
Oh yeah, so if you have the details on it, I'm happy to discuss this with you. So yeah, come find me after the talk and I'd love to chat to you about that.
Okay, the other thing is, I'm not sure about this overlay thing. Isn't that possible to switch it off as a setting?
So that is a good question. So when an app defines this particular permission, by default it is granted the permission to draw over other apps. So if you want to prevent that kind of overlay attacks, you need to go into the settings, Android settings, and explicitly disable that. So prevent this app from drawing over other apps. So I think there's a bit of discussion to be had there about this particular design. Inherently, you should prevent apps from drawing over other apps. But the way the Android ecosystem has evolved, they want to ensure there's backward compatibility. So developers who have built apps for older versions of Android shouldn't be penalized because you've now made a design change. But in lots of my work reversing Android malware has been around these kind of overlay attacks. So I think maybe there is an argument to be made that, okay, this is a bit of a dodgy permission, and by default we should disable that.
Okay, but what would be the use case for an overlay?
So lots of apps like Facebook Messenger uses overlays. So you know when you use Facebook Messenger, you have the little bubble that's over every other system activity. So yeah, so that's one of the use cases of overlay.
Hi, just with the system overlay permission, by default in Android 7 it's been disabled, and you have to specifically enable it on a per app basis. So it's a case of from 7 onwards, certainly on Huawei devices, HTC devices, and Samsung devices.
So is this
the draw over other apps permission is disabled by default, and you have to specifically enable it per app.
Okay.
And
so
also now you get a persistent notification saying that an app has the permission to draw over other applications, certainly in Android 8. So it's a case of there has been quite a lot of work seemingly on reducing the possibility for overlays, overlay attacks, by the fact that you get persistent notifications and specifically have to separately grant a permission that can't be requested at install.
Okay, so that's interesting because the demos that I just showed you are on, so these were on Pixel devices running Android 7.1.2. And it didn't prompt me to enable the overlay permission. All these apps define that. And at no point was I prompted to enable this particular feature. So I'm not sure, maybe this is a specific thing to some vendors. So I believe Samsung, they have a protection in place that prevents you from drawing overlays. So I don't know if it's something that vendors have taken the initiative to build this kind of protection by default in their ROMs. But yeah, I'd be interested to chat with you more on what the specifics are of that particular version.
Cool.
Any more questions? This is my favorite bit, answering questions. Okay, let's go. Thanks, guys.